you're just happy. We are getting close to the end of the lectures, and then you can have the real fun. Okay, good. Then when the discussion that we had thus far is essentially for general purpose computing, and caches are still utilized in embedded systems, but there are a couple of issues which preclude or limit their utilization. Then if I have, don't do that, you'll have troubles with your joints later on. I don't know who did it, but I heard the noise. Then later on you'll have hands like that. You could not drink the coffee. Then one issue is when I deal with real-time systems, I want to be sure that I can deliver the goods before the deadline. If the cache would have been predictable, cache would have had no problem. But cache is not predictable. I have a miss rate probability. Then I have to do something. I have to do a worst case analysis in order to be sure that even in the worst case, my application will be able to deliver the goods before the deadline, which complicates the things. The other disadvantage is that most of the time embedded systems are energy confined. Then I want to run, actually today, what we dream for are zero power systems. Now, zero power systems, it doesn't mean that it's a perpetuum mobile. You get nothing out of nothingness. This is not possible. A zero power system, or maybe you can invent that, you know, I put all my trust in the future generation. And you solve the problem of the energy. Then what that means is that I have limited resources of energy in a battery. I have some facilities to do scavenging from the environment, then get energy from the environment, store it in my battery, and then run the system, run the application until the application is obsolete without any kind of power supply service. And this is a use case for many things like, you know, wireless sensor networks. Now we speak about body area networks. You know, in the future we will be full of sensors, and our body will talk with the central computer and will report, I don't know, the temperature, the blood pressure. We'll even talk to each other via those computers. We will not have to talk, right, any longer. Brain communication. Now I'm pushing things towards science fiction. But basically, in such a system, I want to save all the drops of energy which I have. And for that reason, a cache might be not a good option. And traditionally, in embedded systems, we have a kind of buffer, memory buffer, which is called scratchpad. And the programmer takes care that I have the data in the scratchpad whenever I want them. Then I'm doing loading of operands and loading of things that I need in that scratchpad under the control of the program. Which means now I can do an analysis on the execution time, and I can guarantee deadlines, and everything will be brilliant. I will not have misses. But if I change a byte in the application, the entire construction will fall down and I have to redo the analysis. And that's the reason why today in embedded systems we are also kind of going towards caches, but with some limitations. We are trying to partition them, to diminish the interference between tasks, for example. Then I can have a cache, and I can say, you know, this part is only for task A, and this is for task B, and there is no way that they interfere, and then the predictability of the system, it's improving. This is what we call compositionality. Then I put tasks together, I They are well characterized. I know their time behavior. When I put them on such a system, the interference is small, and then I don't have unexpected behavior. Okay, this is a summary of cache optimizations. It's about what I can do in order to improve things. And what you can see is that some of the measures do have positive consequences on some aspect and negative consequences on other. What I also see is the complexity. 0 means easy, 3 means difficult. This is just an overview. And somehow we finish the story with the cache. Then there is only one more ingredient that needs to be addressed, and then you are processor gurus. Okay? No, but this is true. You may say we don't really know the details, which is true. But the concepts are more important than the details. The details, you can work them out in an implementation. But if you don't grasp the concept, then you cannot do a good job. Now, virtual memory relates to another kind of situation, and it's related to this. Then it's related to the communication between the memory and the disk. And why we call it virtual memory? Because it creates the impression that you have actually more physical memory in the main memory of the system than you actually have. It's a sort of buffering again, but now it's going on between your main memory and the hard disk or whatever kind of flash memory you have. Everything is the same, conceptually speaking, plus or minus, but some details do change the strategy. And things do happen now mostly at the level of the operating system. While you see, we were discussing about the CPU looking for data or for instruction in the main memory and getting those fast from the main memory via an intermediate buffer or with other levels of caches. Now we are talking about the communication between the down part of the system. Because it may happen, and it did happen a lot in the past, that the virtual address space of an application was actually a lot larger than the physical available memory in the system. Then let us assume that my application is huge and I need, I don't know, 64 gigabytes of memory for that application. That's the address space and that's the application. But my physical memory, it's only 16 gigabytes or only 2 gigabytes. What do? I still can run, but I have to create a mechanism of loading in the main memory what we call the execution set of the application, and to put the rest on the hard disk and to bring it in the main memory whenever we need it. In the same way we are bringing from the main memory in the cache information, we bring now from the hard disk to the main memory. The things are similar, but somehow different. Because now we speak about different kind of... Where is that table? It's not here. Okay. It was a table, but it's later on. It's here. Then now we speak about different kind of numbers. Okay? While when I was looking in the cache for a hit, I want one cycle. Usually, in the virtual memory, we talk now about hundreds of cycles, thousands of cycles. Then those are slow things, and they are done under control of the software, of the operating system. And this is not really contradicting what I said. Concepts are similar. Boundary conditions do make the decision different, then some things I will have to do in a different way due to what I call boundary conditions. Okay, now let us return a bit to the, oops, yeah, it's the wrong direction. I never understood how this is moving. Okay, then the same principle of locality, but now I'm looking about the communication between the main memory, which we said it's a dynamic RAM system, and the big memory, the storage, which is a physical disk. Okay, I told you about that. And this is basically what I should be able to do. Then I have my virtual memory, which is the application space. And that's my physical memory. What I do is I partition my virtual space in what we call pages. Probably you saw that you get sometime errors from the execution that you have a page fault, right? Okay, this relates to this mechanism. The page fault is coming from here. Then practically the operating system is doing a management and is doing a address space translation. But now that one is done at the page level. And what you see here is the virtual memory. You know, there are 4 pages. And each page can be located anywhere in the memory. Then from that point of view, we deal with what we would be called a full associative structure. Because the main memory now is like a cache over the disk, but it's full associative. The assignation of a page into a physical space in the memory is not done as before with some bits from the address. No, the operating system will say page A will go at that location, which is, you know, from the start point of the 12 kilobytes. And page B will go to that location, page C will go to that location, and page D, because I don't need it, will stay on the disk. That kind of table with the mapping of pages is maintained by the operating system. And each application which is running has a different table. And the operating system now has a job to provide to all the application the working set in the memory. Because when I'm looking for a location and it's not in the memory, let's say my application will look for page D is not in the memory, and I will get a page fault. Which means I have to load it. From the application point of view, that will be a catastrophe, because this will take many cycles. Luckily, we operate in an environment where more applications are running, and the processor can still work. Then while the page is loaded to the memory, the processor can do other things, okay? Now, as opposed to the cache situation, now my physical memory is full associative. Then the location of the page in the main memory is not limited. What you can see already is that I create some kind of fragmentation in the memory. There are parts which are occupied and there are parts which are not occupied. If in this case, you know, it's not relevant. And in this case, I could also put page D in the memory with no problem. But when there is competition for the memory, it's good to be able to utilize it in a proper way, such that all the applications will get the pages that they need in the main memory in the same time. Okay? Now here we have some kind of terminology. We went a bit on the virtual address and on the physical memory. We went on the address translation. The only thing that we didn't really talk is about page or segment. And I also said something about the miss, which is now called a page fault or an address fault. But it's still a miss. Okay? people are using terminology sometime in different ways, then you have to be sure that you really understand the meaning of things. Yes?
But if the data is so scattered about the memory, then you can no longer use locality for loading in extra data from the memory.
I don't understand.
Well, use locality to predict which.
But within a block is not smaller. A block is a large chunk of a program.
Okay.
And then the cache is actually working all over the block. And it doesn't have to be scattered. You can put it also next to each other. That's just an example. Then a block, it's not a small, remember I was looking for this diagram. You see, in a cache, the cache line has anywhere between 16 byte to 128 byte. In a virtual memory, a block can have 64 kilobyte. Then it's a big chunk of the program that you load in the main memory. Okay? No, I won't excuse you. Why would I excuse you?
I have a question.
You have a question or you have a doubt?
It's kind of a question.
I know people from your culture, they usually have a doubt. I don't know really why you prefer to say I have a doubt instead of a question, but you may ask.
The question is like the use case of a processor, we could have like multiple processes, and there could be an instance when a lot of pages between these processes are common, the contents of a page. So is there a, are we merging those pages or we are keeping separate instances of same data onto the memory?
Then each process has a translation table which is specific to that process. The operating system is keeping the bookkeeping, is doing the bookkeeping for each process. And whenever the process is active, it takes care that the pages are in the main memory, and then the process can execute. When there is a contention, you know, depending on other things, we'll make a decision. Who can execute, who can stop, and how to do the page allocation. Then the operating system is now in charge and is doing an analysis, and you see, it won't make sense to give you page in a memory when you are actually waiting for an input-output event, because you are not executing anyway. You know, you wait for data coming from another, I don't know, from an instrument. If you don't have the data, why would I give you a page? Then this is happening also in Windows, okay? Even Windows has that. No, but most of you probably are Linux fans. You know a bit about Linux, okay? Then part of the Linux, there is a kernel which is doing that page management. And is giving, depending on many other things, is giving different priorities to different applications, and is managing this translation process. Okay. Now, where I was, no, oh, we were, no. Okay, we were here. Now, again, looking at this table, we make a comparison between caches and virtual memory. Then cache is relation between cache and main memory. Virtual memory is relation between main memory and disk. Can be solid state disk, doesn't matter. And what we see is that there are things which are common. The numbers are very much different. The cycle times related to the management of this virtual memory are a lot. We deal with thousands, maybe millions of cycles. There are also issues related to the replacement policy, because as the cache can be full, the main memory can be full too, and you have to evict pages. Okay. Well, it's something which I mentioned already. You see, in a cache, you use a number of bits from the address in order to do the address in the cache. In virtual memory, you don't do that. Because all the memory, all the address, it's actually a tag. As it was in the cache, a part of this address, due to the fact that you have full associativity. Okay, now, there is one story, you know, when I am doing page allocation, sometimes the application is not utilizing the complete page. You know, the page is something which I defined at the hardware level, and it is decided to be, I don't know, 64 kilobytes, but my application may have a kind of different structure, and I have two possibilities. The logical segment in an application is smaller than 64 kilobytes or larger than 64 kilobytes. Now, if I really want to utilize the memory in the most effective way, I should go for what we call segments. Then I'm not transferring a page from the hard disk to the main memory, I'm transferring a segment where I have the start address and the length of the segment. Then a segment can be seen like a page with variable dimension. But now this will utilize the memory in a better way because I will not leave some kind of empty places in the memory, but somehow will make the transfer process more complex because I have to deal with an extra parameter. It's not by definition 64 kilobytes the transfer. It will have a certain length. And both ways do have advantages and disadvantages. And one compromise, which is usually utilized, it's a hybrid approach. You go for segments, but you kind of embed them in an integer number of pages. Then if your segment is shorter, you send one page. If it is longer, you send as many pages as required. You make the page small in order not to spill memory, and you send a number of pages which is covering the logical segment in the application. Yes. You have too many questions. I don't like that.
So what decides the size of the segments?
The segment is decided by the application. Then the application may have a logical part, you know, I'm executing this task, and this task is long as this, and another task is long as that. I don't need both of them in the same time in memory. I'm even, let's say I'm even doing audio or I'm doing video. The length of the task is different. I can see that as a segment in the application. The page dimension is decided by the hardware, by the interconnect between the hard disk and the main memory. You know, how is the bus organized? What is the architecture of the disk? You know, how large it's a block of the disk. And that's kind of determining the page. And the hybrid solution is trying to make both parts happy. Not to spill memory, in the sense that you are loading a page and you are using only 10% of it. Then you make page kind of smaller and you use more pages in order to get a segment. It's a compromise. Now, systems may work one way or another, and depending on what you execute, on how your hardware is, you know, your hard disk and your interconnect bus is looking, you may have one or the other. Okay. You see here you have comparison between page and segment, and you can see very easy that there is no good solution. Each of them has pros and cons. If I look at the page, it's fixed dimension. Then simple is better. You know, in design there is a concept which is called KISS. Keep it simple. The second S we don't talk about, right? You know the full story of the KISS? It's keep it simple, stupid, right? But then this page, it's okay, because it's okay. Replacing a block is simple, because it's just fixed. When you replace a segment, you deal again with complexity, because the length of the segment can be variable. Okay? Now, let us look at the translation process. Then basically you generate a virtual address. The virtual address will go to a hardware mapping block, and then you get the physical address, and the physical address can be utilized now in the hierarchy. This is done with a combination of hardware and software. And as I mentioned before, each program has its own virtual address. And I have some other complications now because I have to protect programs one from each other. And the operating system is the master. It's actually deciding who is going into the memory, who is waiting, and what other kind of things can be done. Now, as you see, in the virtual address, I have 32 bits for address, then my address space is 2 to the power 32. And in my physical system, I only have 30 bits. Then it's narrower. What I do is I use a translation mechanism which will translate the most significant part of the address, which will give me the virtual page number, and I'm splitting my space in pages, and the pages are, how large is a page now?
20.
It's 10 bits, then 2 to the power 10, 1 kilobyte, then I have pages of 1 kilobyte, and I have that many pages. And now what I'm doing is I'm looking in the physical space where I have again 1 kilobyte pages, but less pages, okay? And I do the translation. The physical offset within the page will be the same, because I'm taking a chunk of the program from one space and I'm mapping it as it is in the other space. It's isomorphic translation. I'm not, doing any kind of change in the logical structure of the program. If I do that, then I execute a different program, and I have to preserve that. Then, practically, what I have to do is I have to do a lookup in a table. Then I use those 21 bits. I go in a table, and from that table, I get the other 19 bits. Or 20 bits. And that's the principle of the translation. It's just a lookup in a table, but the table is pretty large. Okay? Now, then I take the virtual page number, I look in here in that one, and I get that address, the physical page number, I take the offset, and I'm done. Now, what you see here, and it's not said, it's a first column, which will tell me something, and that something relates to validity. And in here I have more complications because there might be access rights to the page. I may be allowed only to read the page, or to read and write the page. In which case I would be only allowed to read the page. Yes?
Maybe if you share it with another program or the operating system.
Okay, that might be a case. Then, if that's due to the logical structure of the application that I'm executing, I'm just reading from a FIFO.
And code page.
The code page, okay. That was the one that I was referring. I was thinking about, but also the first one, it's okay. Today, applications are done with that philosophy in mind that you cannot change the code while you are executing. Some years ago, that kind of things were happening for protection, but also in order to utilize the resources in a better way. Then while executing, you could even change the program that you were executing. But today, we don't allow for that. Then a program is not changing itself, You cannot do surgery on yourself. Somebody else should do that. Okay, and now what you see is that I have what is called a page table based register. And this is a hardware facility in the processor. It's a register which will tell me the start of the table that I have to look for. But this table is not any longer a cache or something like that. It's located in the main memory. It's a part of the main memory which belongs to the operating system. And then whenever I'm dealing with application 1, I have to look for the base register address for application 1 to load it in that register and do the lookup there. If I'm changing to another application, I have to update the content of the register and then look in another place. Then what you see is that that kind of address translation requires two accesses to the memory. Then each and every access to the memory will result in an access in this table, which resides in the memory, to get the physical address, and then another access into my memory to look for what I want. Then practically, if I'm not doing it in a smart way, before going to the cache, I have to make an access to the memory, to the main memory, which is not really something nice, right? It's not nullifying completely the efficiency of the cache, but it's not nice. Now, that's the reason why I postpone it. Remember the structure with postponed calculation of the virtual address, or I do it in parallel. But there is more than I can do. I can do that also in a kind of cached manner. Then, not to keep the entire page table, but to keep a cache over the page table, and then to speed up things, you know? Now, the complexity may get a bit out of control, but the concepts are similar. Just, you know, I have to deal with the complexity in the proper way. And this is my page table now for the example that we had before. You see, at location 0, which is the index of the virtual memory, I have a valid page. 1 means that it is in the memory, and it is located in a physical page 3. 1, 0, 1, 2, 3. Okay? Then page B, then, which is also valid, and it is located in physical page 1, 0, 1. Page C is in physical page 5, and page 3, virtual page 3, it's on the disk, and then it has a 0. And that table, the operating system has to update depending on whether or not pages are resident or not in the memory. And I also have to be sure that whenever I take a page out of the physical memory, I write on the disk changes if they happen. If that page was an instruction block, then code, I should never do a write. But if that page relates to data, I may have to do a write. And in this case, you see that I don't have write through. It's only write back. It doesn't make sense to do write through, because you deal with a large part of a program which is essentially keeping the execution set for the application in the main memory. But when you edit the page, you have to update the data on the hard disk, because next time when you load it, you will not have, you know, the results of your previous calculation in the main memory. Okay. I told you that. Then I told you about changing the table. Okay, then this is a bit of a zoom in the page table now, which contains a part of the valid bit and the physical page number, also the access rights. which we also covered already. Those are typical things that you know also from files. When you, in Unix, you see if you can read, write, execute, you do that with change mode. In the same way you have it here for pages. You cannot do it as a user, you know, from the command line, but in the application, you know, the application developer can determine what segments can be changed, what segment can be read when sharing things between tasks, and the operating system also has that kind of protection in order to preclude spurious interaction between tasks. If things are going wrong, you should try to avoid a fundamental damage. Okay. Now, virtual problem 1. Okay. We already discussed that. Then I have physical memory, which is smaller than the virtual memory, and I have more tasks which are sharing that. And we go for what I mentioned already, which is the working set. Then the operating system is taking care that at each and every moment in time, each application should have present in the memory the working set. Working set means all the pages that I need in order to do the execution for now and for the close future. Now, the operating system can also try to predict things and to help me to prepare things for me in the future. But also when things are going out of control and I don't have a page, because more applications are executed in the same time, I will stop the execution, other application will get the execution, and the operating system will bring the page. Okay. Okay. Now this is one of the important parts. I mentioned a bit, and it's about the fact that each memory access now has two accesses. One is to the page translation table, and the other one is the real access. In order to deal with that in the proper way, what you do is you rely on the same principles of locality and you remember the previous translations. Then you will make a cache like structure, which is called translation look-aside buffer, has a different name but has a cache behavior, where you store the previous translations. Now, instead of accessing the page table in the main memory, you first look in this buffer. Then what you do is you look in this buffer and you do the same kind of comparison. If the translation is available there, you see you have the page number, you have some kind of auxiliary information about the fact that this is good, this bad, access rights and things like that. And you do like in the cache. If you find a tag there, this means that you found already the translation. You take it, you don't go to the main memory, and you just go to the cache for your access. If it is not there, then you have to do the translation. And this is the structure for modern memory systems in processors. And things are going as I said. The processor will issue a virtual address. That virtual address is in the space of the application and will go to the TLB. The TLB will give you the address of the physical page where you have to go, or will say, I don't have it. That is done on a tag comparison, like in any other cache. Then I compare a tag. If it's valid and if all the conditions are okay, this will give you the physical address. If it's not there, you will do the access to the page translation table in the main memory. You will get from there the address, and then this means that you will have some extra delay, but you will also update the TLB with this new address, because eventually you may need it later on. Then if the hit rate is high, this kind of translation is hidden, except for the compulsory kind of misses. It's very much the same as for a cache. Now, after you solve that, then you got from the virtual address to physical address. The rest you already know. You look in the cache, miss, hit, whatever. You go further. Okay, this is an explanation of what I just told you. If the page, the physical page is not in the TLB, you have to go into the translation process. Then this is again an explanation of what's going on. Now, it may happen that you have a page fault. Then the data is not available. Did I say it right? The data is not. Yeah? Sure? No. Data, it's a Latin word. It's plural. It's datum, data. Most of the engineers and most of the people working in this field are analphabets. They don't know that. Then if you want to say it correct, it's data are. It's like automaton, automata. Datum, data. Don't look at me like that. I'm just, yeah, you, huh? No. Yeah. I'm just trying to educate you. That's my job, right? It is established in the community to say data is, but is grammatically not correct. Because data is coming from, as a word, is coming from Latin, and it's plural by construction. Then we should say data are. You say data item is, and then it's correct. Now, if you don't find the data because the page is not in the memory, you will go into an even longer process. And that process will be, now you give up on that application for some time, for a long time actually, and you call the direct memory access part, you know, it's a functional unit in your system, which will take care of the transfer of the page from the hard disk into the memory. Then the DMA will become the master of the bus, will do the transfer between the the disk and the memory, and then you can continue executing other things. And eventually when the DMA finish the transfer, you can resume the execution because the page is there and you can start your execution further. Then you see, as opposed to the previous cache where you had hit and miss, now you have more complicated things, and they may go from very fast translation to very slow update of data from the disk to the main memory. But conceptually speaking, it's the same. Details may kill you in practice, but concepts are similar. Okay. I think we should stop in here. I know. Okay, then please send me emails. Actually, why would I say please? It's your responsibility.
Yeah,
Don't
sure.
do it. You don't